It's a pleasure to have Gian Giudice visiting the Colloquium today. He's actually been visiting the particle theory group for the whole week. It's great to have him and our other friend from Europe, Ricardo Vitazzi. Gian got his PhD from the University of Padua. He then did postdocs in the US at Fermilab, and then at the University of Texas, Austin, in the group of Steve Weinberg, the giant of modern particle theory. He then went to CERN, where he still is, and he worked his way up through the ranks. In 2016, I think about then, he became the head of the theory group at CERN, the home of the LHC. And he has won, well, he has got many awards and honors and honorary chairs here and there. He is a member of the Accademia dei Lincei. I hope I'm pronouncing that even vaguely right. With one of the top honors in Italian science. I've known him for many years, and he is one of the pioneers of many directions in particle theory in the last quarter century or more. He has pioneering papers in understanding the Standard Model and its vacuum stability. He has pioneering papers in the phenomenology of what it means to see extra dimensions using particle colliders as the microscope, in the theory of supersymmetry breaking, in the theory of the possibility that the Higgs is a composite particle. I noticed yesterday that he had maybe 9 papers with more than 1,000 citations, so his work, and that matches my vague impression, which is that his work has sort of defined so much of the agenda of particle theory in the last quarter century, and 16 papers over 500 citations. Okay, so just massively cited, huge reputation in the field, and he is a member of the directorate of CERN leadership. So today, I can't think of a better person to speak to us and address us on where is high-energy physics heading to from the viewpoint of CERN. Thank you. I should say he's written apparently 2 books. This is one of them that he sent me a few years ago, called The Zeptospace Odyssey, which is a popular layperson's guide to the physics of the LHC. I had to look up what zepto meant. Apparently, when you get to the femtometer level of size of a proton, and you go 6 orders of magnitude smaller than that, I think you get to the zepto scale. And he's written a book on cosmology recently, which I hope soon will be translated into English. Anyway, sorry.
Thank you very much. It's been a fantastic week, really a great honor to discuss with some of the greatest theorists in the world. And thank you very much for the hospitality, in particular to the theory group. So I was assigned as a homework to tell you the question that was asked to me was where is high energy physics heading to, especially from the point of view of CERN. So I will tell you a little bit what are our questions in the field, and in particular, how is CERN planning the future and how to address them. So the LHC, of course, is the starting point. The LHC is performing fabulously. In the last run, there was records of recorded luminosity, twice the peak luminosity at twice the design value, and together with a high availability of stable beams, this has done this tremendous success. You see here the curve of the integrated luminosity for this year that has beaten every record. So we are talking about numbers. Maybe if people are not familiar, what does it mean? This femtobarns, let me just say that this corresponds to a recording of 3×10 to the 16 proton collision and 20 million Higgs bosons. So it is really a fantastic machine, and this is together with spectacular detector performance. The two main detectors I'm showing here have a fantastic recording efficiency. Recently, one big change was we defined a new schedule for the LHC. The reason was that there were some delays with the preparation for the high luminosity phase, which required some change in the schedule, which means that the current run will be extended. This was supposed to finish in 25, will be extended until the end of June 2026. But then also the long shutdown 3 has been extended in order to allow for the completion of the preparation of the high luminosity and the upgrade of the detectors. So altogether, this means that the high luminosity phase has been delayed by 1 year, and the physics run will really start in summer 2030. I must say this was a very painful decision, because even if, in usual construction, one might say, well, 1 year, so what? We are very careful at CERN always to maintain schedule, maintain within cost, and in particular now that we are discussing about future machines, it's very important to show that we really maintain every schedule. However, also we have changed, and the long shutdown 5 have been suppressed and replaced with a end of the year technical stop, so which means that the target of 3000 inverse femtobarn of luminosity will still be reached at the same time that was originally predicted. So it means that in 2041 this will be completed. The LHC has the results of the LHC have radically transformed our view of the particle world. First of all, these results have given really a comprehensive exploration of the standard model. Just to give you a picture here, I've shown the cross-section of various possible channels, and they span over 13 orders of magnitude. It's really fantastic that you can reach all this accuracy in very, very different processes, and this is thanks to the fantastic performance of the detectors and the machine. This means physics results. So there is a high precision measurement of alpha S, there are high precision measurement of the cross-section for W and Z, and then of combined anomalous couplings. Very much advertised. It's been, you see here on the top right, the measurement of the W by CMS has reached a precision of about 10 MeV. Okay, this is remarkable. You see, remarkable, especially when you compare it with LEP, which is the top line. You see how much improvement. LEP has always been advertised as a precision machine, and with the LHC, one can really do much better, and also has ruled out the CDF measurement, which was predicting a large deviation from the standard model. The high luminosity phase will expand this exploration of the standard model significantly. Here I'm showing how many events will be produced in the various channels. We're talking about almost 10 to the 12 Ws and billions of TT bar and so on. And so this really means a lot of precision physics that will be reached in this phase. In particular, for instance, the error on the W mass and the top mass will be cut by half. Higgs physics is, of course, an important part of the menu. I think it's very remarkable that in only 12 years, 12 and a half years, we went from the discovery of this particle to doing precision measurement of this particle. This is really, in times of particle physics, it's remarkable how fast it went. For instance, like the Higgs mass now is known as the per mil precision. It's better known than the Newton lifetime, which is such a familiar thing in particle physics. A good way of expressing the result is this plot that shows the coupling of the Higgs to various particles as a function of their masses. And you see again, we are talking about scanning over 3 orders of magnitude, and the success is perfect, which is a clear proof that the particle discovered acts like the particle that gives mass to these particles, the particles in the Standard Model. The precisions in the measurements of the Higgs coupling is usually expressed in terms of a coefficient in front of the vertex. This is, of course, for a theorist, this very odd way of doing it because it doesn't even respect gauge invariance, but it's a very convenient way for experimentalists to translate their data. And at the moment, we have a precision on the coupling to gauge bosons of less than 10%, couplings to the 3rd generation family of the order of 10%, and we even a 20% accuracy on the coupling of the muon. The high luminosity will go to the level of the percent. So it's a significant advancement. For the gauge boson, you see it's 1%, maybe a few percent for the fermions. We'll also, can also test the coupling to charm. So we go into 2nd generation. Of course, this is more difficult, a large background, the difficulty of C-tagging, but nevertheless an order 1 measurement, and also an order 1 measurement of the self-coupling of the Higgs. The 3rd big message from the LHC is that we haven't seen any signal for new physics beyond the Standard Model. Here I'm showing some plots that tell you that, for instance, gluonons, quarks have been ruled out at the level of almost or more of 2 TeV. I can show you, this is a summary of the channels. I put it small enough that you cannot read, exactly because you should not read it. It's just to impress you of how many channels have been looked for. So really a comprehensive search of new physics, and the limits range in between 1 and 10 TeV. So really way beyond what was the theory expectation for new physics. So one could ask, okay, good, you've been extremely successful with the LHC. Is this the end of the story? So has now the high energy physics program been completed because you answered the question that you wanted to ask? Well, I mean, the question is, now we can go on and do a more precise measurement, but does that make sense to make a more precise measurement? And when in physics, you do measurement not simply because you can do it, but because you want to address some fundamental physics questions. So why do we need to go further beyond the LHC and explore? I'm trying to summarize the reason in terms of mysteries. So the first mystery that we are facing is the mystery of the Higgs. If you look at the Standard Model Lagrangian, you see that there is one sector which describes, let's say, from gravity to the fundamental forces, which is very satisfactory, because just coming from a principle, you can describe completely all the phenomena that you know with very few free parameters. That's exactly the dream of fundamental physicists. When you go to the Higgs sector, the story changes radically. To explain the pattern of quark and lepton masses and mixings, yes, you can do it with an appropriate coupling called Yukawa coupling, but you need to introduce a lot of free parameters. Essentially, actually, not only one per observable, even more. There are some redundant ones. When you look at the quartic interaction, you find out that within the Standard Model, you create an instability of the vacuum. You have a naturalness problem. I'll talk about it. And if you wish, a cosmological constant problem. So in a sense, that is where all the problems that we know of the Standard Model, the structural problems, come from this Higgs sector. And if you wish, one of the reasons is that these interactions are gauge invariant, but they're not purely gauge forces. And when you do that, you lose the beauty and the simplicity of gauge interactions. So the take, for example, the Higgs potential. The standard model Higgs potential is today one of the best measured quantity that we have in particle physics. The precision is really fantastic. I mean, the Higgs potential depends on two parameters, and we have measured with a precision of 0.1 or 0.1%, right? You translate it in terms of Higgs mass and the Fermi constant. And yet, you say, well, okay, you must be satisfied by that. Yet, as theorists, we are not, because this description looks much more than a parameterization of the phenomena rather than an explanation of the phenomena, dynamical explanation. It is in a sense like what the Landau-Ginzburg model was for superconductivity before BCS came and before we had an understanding of the phenomena. So this is to say that with a sufficiently large number of free parameters, the Higgs can accommodate all the observations that we know, but it does not provide what we call an explanation of it. And since physics, fundamental physics, is not only about describing how nature works, but also explaining why it works that way, we are still not satisfied by Higgs, by the Higgs. Certainly, the Higgs boson, why is so important the discovery of this particle? I mean, it's not just because we discover a new particle, but because we discover an unprecedented phenomenon in particle physics. And we are facing some problems that we do not encounter with other particles. Does this Higgs actor, why does this Higgs actor lack this uniqueness of the gauge sector? Why there are these non-gauge fundamental forces, the naturalness problem? Is this particle fundamental or composite? How do you generate the quarks and lepton masses? And also, in the way I describe it, the Higgs can be a natural portal to new sectors in the sense that it contains the only Lorentz and gauge invariant term that you can write with, which is super renormalizable. So you can naturally attach it to some dark hidden sector. Also, certainly the Higgs is deeply related to the history of the universe. It described the space-time vacuum structure. There is this issue about the metastability, and so for the ultimate fate of the universe is, if you wish, connected to that. It's a prototype for inflation and a prototype for early universe phase transition. So understanding better this phenomenon could lead us to understand something. So I think there are many good reasons to say that the Higgs precision is a not to be missed experimental program. Can I quantify what we learn from Higgs precision? One example is if I take that the Higgs is a composite particle, and I can roughly see that the deviation of the Higgs coupling with respect to the standard model scale like 1 over f, where this f parameter is associated with the compositeness scale of the Higgs, and measuring at the level of 0.1%, which is the future machines, could reach a sensitivity to a scales of 100 TeV. So this is very remarkable. Let me just express the same thing in another way. Let me define a degree of compositeness of a particle as the size of its structure in units of the Compton wavelength, which is a measure of its quantum size. So for the proton, if I do this exercise, I find that the degree of compositeness is 1. And this is an agreement with the notion that the proton is a fully composite object. For a pion, if I do the same exercise, the pion is a composite particle, but also emerges as a Goldstone boson. So it's something a little bit in between, and I find a value of 3 × 10⁻². So with today's precision, we have attested the degree of compositeness of the Higgs up to the level of 10⁻², so less than the pion, which means that the Higgs boson could be as composite as the pion, and still the experiment would not see anything strange. So the future, with the future Higgs precision, we will test compositeness at the level of 10⁻3, and so we go beyond. So the frontier for the Higgs is precision in the Higgs coupling, really going down into the core of this particle, testing second and first generation, hopefully, to test this idea of flavor, possible invisible Higgs decay, maybe they are related with these dark sectors, the Higgs coupling, which is directly related with electroweak phase transition, test of rare decays, which probe a new kind of physics. So this is a broad physics program that really touches all the aspects of all the problems that are related to electroweak breaking and the Standard Model. And indeed, this was identified as a priority by the 2018 European Strategy for Particle Physics. The second mystery is flavor. Why the quark and mass and lepton masses are what they are. Clearly, there is a pattern, but we have, at the moment, did not find a good explanation for this. This is, I would find, the most embarrassing aspect of the Standard Model, that we don't have much knowledge, even if the experiments have given all this data. And you see that when you introduce the Higgs, you see that this flavor problem is really related to the rest of the theory, which means that you cannot really decouple the measurement of, let's say, electroweak data, Higgs couplings, flavor measurement. They're all related in a theory. They all give complementary information and should not be treated as independent. Unfortunately, the difficulty with the flavor problem is that we cannot anchor it to a specific energy. All we can do is test the theory as much as we can, hoping that we could reach it. And also, almost any theory that you can think that tries to address the issue of electroweak breaking almost necessarily disrupts this fragile structure of the flavor which is present in the Standard Model. And indeed, for instance, high luminosity will have a significant impact on flavor measurement. Here on the left, I'm showing the improvement in the fit of the CKM parameters. On right, I'm showing that the B0 mu mu decay, which can test new physics, will be measured for the first time. Then let me call it the third mystery, the mystery of the unknown. We certainly, the Standard Model is an amazingly successful theory, and yet should not be, it's hard to imagine that to be the final theory, because there are many considerations that tells you that the theory is incomplete. Now, on the theoretical side, aspect like we don't know what quantum gravity is, what is the structure, why the structure of the gauge group is coming, why are the repetition of families, neutrino masses, Higgs naturalness, electroweak stability, vacuum energy, they're all issues, even if they're not related with a conflict with data, but they are structural problem of the Standard Model. And then on the cosmological side, what is inflation, dark matter, dark energy, baryon asymmetry? I'm not saying that a collider can address all these problems, obviously, but I'm saying that we know that there is some structure beyond, and the only way to proceed is to continue this exploration, because we have good motivations to go after at least some of these problems. I have mentioned several times Higgs naturalness. So let me explain very quickly what it is. The idea is that in a quantum field theory, the quantum correction push mass parameters to the maximum values allowed by symmetry. In a sense, quantum mechanics acts like anything that is not explicitly forbidden is allowed. It's a very liberal idea of a legal system, and then the problem is that since the scale is pushed, it means naturally that the UV cutoff, I mean the scale at which new physics should appear, is not very far from the scale of the Higgs mass. And this is why naturalness really anchors the scale of new physics to the weak scale. However, today we are facing three problems. One is, I mean, we have three pieces of information which are in a sense confusing. One piece of information is this: natural tells you, okay, the new physics scale should be relatively near. However, when you look at the theory and you see that the standard model has a certain number of accidental symmetries, accidental conservational laws that suggest, on the other hand, that the scale for the violation of this should be very high. Proton decay, baryon number, lepton number are conserved to a very high level. And the third piece of information is that the LHC data now exclude a large class of the models that we knew that were able to address these first two issues. So the difficulty today after the LHC, while before we could just construct a model that had those properties, now we have to navigate in this narrow territory full of obstacles that if you go in one direction, you have one problem. If you go the other direction, you have a problem. And so we have to find the way, if there is a way, through these obstacles. So it could be that we still haven't been smart enough or lucky enough, and actually the solution is some of this kind. Or the possibility is that this puzzle is telling you that we need to look for a radically different approach to naturalness. The traditional approach is based, this idea of effective theory that you have separation of scales, and then symmetries rule the difference. And maybe this should be challenged. And this is really, I would say, the revolutionary impact of the LHC, which is reshaping our vision about what it means to search for fundamental principles of nature. Now, this idea of the separation of scale is really part of physics. I mean, Newton could not have computed the orbit of the moon around the Earth with this universal law without using effective field theory and treating the moon as just a point-like object described by only one parameter, mass, and doesn't need to know what is the moon made of, what is internal structure. Bohr could compute the atomic levels without knowing about the existence of quarks and gluons. So we've been accustomed, this separation of scale is the reason why we made progress throughout the century in physics, and we are so accustomed to this description that it sort of seems unavoidable to us. And yet, there are ways, there have been people trying to challenge this idea, the idea that you could push everything to a single scale. One example was in extra dimension, but it's clear that it's becoming harder and harder to reconcile this idea of avoiding scale separation given the data. So the other possibility could be that really the rules of effective field theory completely break down. And so, indeed, you cannot separate, and there is an interplay between something that happens at very small scale and very large scales, and the two things have some dramatic interplay. It's very strange, of course, to think in that term, but maybe there are some examples that tell us that may not be so external to physics. We are used to think that high energy means short distances. Because with higher energies, we can probe deeper into the inner structure of matter. But now consider the case of gravity. If you do a scattering and you go to energy that exceeds the Planck scale, you form a black hole. And its horizon, which is the Schwarzschild radius, hides the inner region of space to outside observers. But the Schwarzschild radius grows with the energy. So the bigger the energy, the bigger the Schwarzschild radius. This means that as we increase the scattering energy, we get less and less information about short distance, exactly the opposite of our usual intuition. So gravity seems to lead to a possibility of IR-UV interplay. And some of these ideas have been also used in the context of what we call it the landscape. that some theories that look perfectly good at the low energy level as an effective theory, in reality cannot be completed with a full theory of quantum gravity. So, so not all the theories that look perfectly consistent with the usual rules of symmetry and low energy are actually allowed to have a high energy completion that includes gravity. And it's said that those low energy theories live in the swampland because they're not part of the real theory landscape. Not all the theories that are allowed by the usual rules of effective field theory, of symmetry and selection rules, necessarily have a consistent UV completion in the context of quantum gravity. And there could be some restrictions in the IR theory that are completely inexplicable from a simply low energy point of view. Of course, this is not sufficient to say that there is an IR-UV connection, but it exposes some of the limitation of thinking only in terms of effective field theory. There is somehow some information which is buried at very short distances that trickles down and influences much larger distances. And this is very unusual perspective, challenges the basics of effective field theory intuition. There have also been attempts which explain this issue about naturalism in a completely different path using the cosmological history and in or within or without a multiverse. But let me, shall I skip this? Maybe because of time, let me skip this. So let me just say that the issues involved are so fundamental and so critical for future developments in particle physics that experimental exploration really must continue. We are addressing some deep puzzles. It's not simply explaining parameters, but structural problems about what is the approach to fundamental physics. I shouldn't remind you that exploration of the unknown has always been driving force in particle physics. Of course, it's not a blind exploration, but it's an exploration that follows some good questions. And I think today we are facing exactly that question. So now that I've convinced you that we should continue, the question is, how do we continue? The European strategy for particle physics is an exercise that started some years ago, maybe not now, but maybe for dinner I can tell you how it started and why. But the idea of this European strategy is to produce the European roadmap in a worldwide context of the field. So unlike the P5, maybe some of you are familiar with the similar exercise in the US, this does not operate with fixed financial scenarios. So we're not trying to say, okay, give us that money, we can do this. But rather just to describe what are the ambition of the community. Does not want to, it's not a decision body. It's just to provide input and recommendations to the CERN Council about the community aspirations on how to advance and what are the priorities in the field, but does not approve projects. So let me quote from the report of the 2020 European strategy. An electron-positron Higgs factory is the highest priority next collider. So as identified, this should be for Europe the next step. For the longer term, the European particle physics community has ambition to operate a proton-proton collider at the highest achievable energy. Ambition, I can tell you that the word ambition was the result of a week of negotiations. So the idea is that we don't say that must be done, but this is charting the future. And Europe should investigate the technical and financial feasibility of this project. And indeed, this feasibility study started immediately after and will be completed in March, ready in time for the next European strategy. So the next European strategy, though, a year ago, we decided with the CERN management to anticipate the European strategy in order for Europe to be ready, given the international situation, early in time to make a decision. This was approved in March 2024. At the end of March this year will be the deadline for the submission of input from the community. In June, there will be an open symposium in which people can come and express opinions, and these opinions will be recorded. It will happen in the most beautiful city in the world, where I happen to be from. And then the important point will be in December, when there will be a strategy drafting session where the document will be a week, where the various representatives go in one place. In this case, the place will be a place in Switzerland called Monte Verità, now which translated it means the Mount of Truth. So you should understand that that document will be certainly represent the truth of the physics. And there, so I participated in the previous exercise, where the various points of view are merged into a final document and hopefully will be approved then in the following spring. So when the CERN Council gave the instruction, they said that the aim of the strategy update should be to develop a visionary and concrete plan that greatly advances human knowledge in fundamental physics through the realization of the next flagship project at CERN. So big ambition and also defining a project, okay? It should define the preferred option, but also alternatives which can be pursued if the preferred option is declared to be not feasible. Of course, the exercise has to be done, but at CERN, we already have ideas of what we want to promote. And the plan A, so the preferred option, will be, according to CERN at least, the FCC, the Future Circular Collider, which is a 91-kilometer accelerator that will, here you see a map, that will also go under Lake Geneva. So there will be two stages. A first stage in which you have electron-positron machine and with study at the peak of the Z, at the threshold WW, at the optimal energy for the Higgs cross-section, and TT bar, top anti-top production. So not necessarily in this order. For the machine, it's the same. So maybe, if Higgs is considered the priority, we could start with the Higgs, then go to the Z, and so on. And then a second stage in which all the magnets will be changed to have a proton-proton machines. If one could use niobium-310 new generation magnets of 16 Tesla, you could reach energy of the order of 100 TeV. One could think of a more modest collider, but it could be reached earlier because it doesn't require high technology in the magnets. Could have niobium titanium magnets like in the LHC. Then you go to 40 TeV. 40 TeV maybe it's a bad number to propose, given the precedent that you had in this country. But also one could dream of even higher energies for the high temperature superconductor. So the timeline for the project is the following. The conceptual design report has already been published. The feasibility study was an important step, and this will be delivered in March. Then there will be the European strategy that will make the proposal. Hopefully, the project could be approved, let's say, in 2028. The construction of the tunnel could start in 2030, so at the same time the high luminosity. This is no conflict for the civil engineering. In 41, say, the high luminosity phase ends, and then the FCCE will be ready for 2045. So this will be a 4-year gap. I think this is very important to decide what is the gap that is allowed, because the risk of having a huge gap between the two projects, there is a more sociological, say, risk of demotivating the community, especially the young people, that they don't see the continuity, they don't see a future, and therefore maybe you can get the money, but once you have the machine, you don't have the people. So at present, say in 45, start for 15 years of V plus E minus, around 2070, you can start with the phase of the hadron that will bring you almost at the end of the century. So the feasibility study that I mentioned, the idea is not to study the physics that can be done, but rather demonstrate geological, technical, environmental, and administrative feasibility, saying the project can be done, and also that the operations are sustainable from an environmental point of view, from a financial point of view, and also societal, the impact on the local communities, and so on, and all these aspects. So it's really a complex exercise that involves very different kind of expertise. So now the plan for the tunnel has been finalized. There's been shown that there is a possibility of tunneling mostly through molasse, which is a rock which is ideal because it's soft for drilling, but also rather stable. And so it's as usual, right? The ring is tilted because of the geography, but on average is about 200 meters underground. And just to show you that the study was really advanced, there's been a significant test of the geological investigations also under Lake Geneva in order to see, well, first of all, get the geology right, but also to see that this is feasible. Of course, there are 8.5 million cubic meter of excavation material that have to be brought to surface, and these are issues that have also a great environmental impact. And just to give you a taste for the level of sophistication of these studies, even the buildings that for the FCC have been studied in a way that they minimize the environmental impact, both from the point of view, the visual point of view, but also the materials used and so on. So for instance, this would be one point where you see the nice rural landscape, and this would be after the construction. And you see that the construction is made in such a way to fit into the landscape as much as possible. Same here. You see that I think it's surrounded by trees, and there is as much green as possible. And so the level, maybe I should move a little fast here. The level of the various aspects from the environmental point of view are very complex, because nowadays this is very different than the time of LAP LHC. We have to respond to society, and we have to show what is the impact on all respect of such a big scale projects. For instance, I was talking about the excavation material, and there are plans to transform it into construction material or even a fertile soil. When it's treated, this molasse could be converted into agricultural soil. So let me forget about governance because of time, but let me focus on the cost. So the cost of the FCCE, I put very precise numbers because this is not just an estimate. This is the result of years of study And so these numbers really correspond to true estimate, and CERN has an excellent track record in doing projects within costs. Assuming 4 interaction points to have 4 experiments, without the TT bar threshold, you get to 13.5 billion, 5 of which are just for the civil engineering of digging the tunnel. And if you add the TT bar, you get to 15 billion. For the Hadron machine, there are not precise numbers yet. This is not done at this level of sophistication, but roughly we're talking about 17 extra billion, out of which 13 come from the magnet. So really the magnet is the cost, once of course you have all the infrastructure. If you would like to go directly to FCC-HH, we are talking about an estimate of 24 billion. So realistically, this is really a factor of 2 larger than the FCC-EE, which is why I say that there are serious problems. It's fairly unrealistic to say we want to go directly to the HH phase, even without worrying about the fact that the technology of the magnets have not been developed yet. So this is why also the costs are just on the estimate. Now, you may say, well, this is a lot of money. Now, is this really feasible? So let me show you an exercise that we did with the CERN management to see, is this project feasible? When I say feasible, of course, the comparison is with the CERN budget, right? CERN budget is 1.2 billion a year, which is given to us, and then we can manage it. Now, the ideal thing would be, well, we can manage it with that money. Of course, such project is impossible. But I want to show you that it's not terribly realistic. So let me do this exercise. I'm taking the 13.5 billion option, the one without the TT bar, and I'm saying that I'm just using only the annual contribution to CERN, the regular budget, with an increase of 1.5% annually for 8 years, okay? So this is 1.5%, is a fluctuation which is of the order of the inflation or actually the exchange rate with the Swiss franc is bigger. So it's something that to me seems within noise. And then I'm adding 4 billion of special contribution from outside the CERN budget. And this is also a very conservative estimate because I'm putting 1.5 billion from non-member states, 1 billion from private donors, which may seem to you a lot, but actually we have already advanced negotiations and pretty much we have almost secured that money. Of course, the money will not only arrive when the project is approved. And a special contribution from the host states, or Switzerland and France, which get a great advantage from the contracts. Now, this is, I think, is a very conservative estimate because already with the EU, we have advanced negotiation and 2 or 3 extra billions are not impossible. So even with this very conservative approach, here the green light shows what would be the situation of the budget. So of course we go in deep deficit, but we would go back to 0 before the end of the FCCE, which means we are ready for another project, say HH, without having any carry forward of debts. So all this to say that actually the project, of course, if I give you those numbers, they look enormous, but then you see that it looks relatively feasible. Such investment have positive returns in terms of technological spin-offs, student training, educational impact. So I would say that it's not difficult to sell to politicians, even if no interest in physics, that this can be interesting and positive investment. Recently, Mario Draghi was in charge of drafting a document for the future of European competitiveness. And it's very important that he spent a page about CERN and identified CERN as a model of international cooperation and successful. And really concludes, say, refinancing CERN is a priority for Europe. And this is not just in a report, because it was echoed by Ursula von der Leyen, the president of the European Commission, when she came to CERN, and she made a speech which was really impressive how far she went in identifying CERN as the place. Basically, every physicist, she said, I'm quoting, every physicist in the world wants to work at CERN. So I'm sorry for you guys, but you are in the wrong place. You should all come to CERN. This is, I'm not telling you, it's Ursula von der Leyen is telling you. CERN is a living proof that science fosters innovation and innovation fosters competitiveness. CERN will change the world. So we have low ambitions. However, and this is very important, I would say, we have, it's clearly Europe is in a phase that they have identified that we are losing ground with respect to the United States and China in terms of competitiveness, in terms of innovation. And CERN and our field somehow has all the right features that can excite these politicians. However, I want to also emphasize for completeness some points which are really written with a strong language in all these various documents, that one of the reasons why these politicians see CERN as the right thing is because of the competition with China. And they're saying Chinese authorities are also considering constructing a similar accelerator in China, recognizing blah, blah. If China were to win this race, Europe would risk losing its leadership in particle physics. And Ursula von der Leyen somehow echoed, we are competing with giants. China is planning this thing. I'm really proud that we are going ahead. This is a very dangerous thing. And I think as physicists, of course, we should please politicians by being careful of emphasizing that we are doing science because this is great science. We're not doing it because we want to compete with China. We want to do it before China. If China does a great project, we're only happy as physicists that this happens. Because I heard also some of the physicists going around repeating this argument, I'm really very much against. I hope that this does not come out from physics, and maybe we should even train politicians understanding that this is not our goal. And the US, what's happening with the US? So in last P5, the US realized that supports an offshore Higgs factory as a priority. They've also identified a budget of 1 to 3 billion in US accounting, which is very different. It's factor 2, 2.5 with respect to the European one. And they're putting they're happy, I mean, you are happy both with the FCCE and ILC. The important thing that happened more recently was in last April of 24, when there was a joint statement between the United States and CERN, in which it said that the United States intends to collaborate on the FCC construction and physics exploitation. Now, there's no promise about money, there are only words, but I think it is a very important document because you see that split the degeneracy. Before, the two projects in Japan and Europe were put at the same level, and now it's a one in Europe that is defined. So we interpret it as a strong indication of where is the future. What happens in China? In China, as you know, there is a similar project going on. There's been a huge technical progress. I think we can go discuss, maybe there's no time, but I believe there are excellent prospects that the project is funded. There's been delay, okay, in this project, so I don't know what to make about these dates. The idea at the moment is to start operation in 2038. Japan also has this project, this linear collider. However, it's sort of in a limbo, and the dates are being pushed and pushed and pushed. I don't know what to say about it. Maybe I'll skip this. So how about plan B? Well, CERN will also propose various plan B. One is a linear collider that has the advantage that can be constructed in stages, so the investment can be delayed as you increase the length. It would start with 11 kilometers, go all the way to 50 kilometers, and have a first stage of Higgs exploration, and then go beyond to higher energy for looking for new phenomena. The problem of these machines is that if you look at the annual energy consumption, it grows very fast with the energy. We're talking about something of the order of 3 terawatt hour. And from it's not only an issue about cost, but it's also an issue about the environmental impact of having machines of that level. So there are various possibilities. CLIC is one. The other possibility is to construct a kind of ILC at CERN. Now there's also the idea has been studied of splitting the beam and having 2 interaction points in order to have more experiments, doubling the experiments. Of course, you're doing at the cost of the luminosity. There is a possibility, instead of not building new tunnels, but use the LHC tunnel, either for a high energy version of the LHC or a kind of LEP3 machine that works like a LEP, maybe with higher energy, but much larger intensity, or the dream of a muon collider that could go to much higher energies. Overall, the FCC is certainly the most complete study when you look at the full project. And if you compare stage by stage with the various alternatives, you find that always the FCC does either better, maybe sometimes slightly better only, or equal to the other options. Of course, there is a big difference that for the FCC, there's been a feasibility study that's been completed. So all these numbers are reliable, while for the other machines, we are only talking about projection. I must say that some people say, well, the FCC is not feasible, then we should go for another collider. I just want to remind you that if this project is not considered financially feasible, the other projects are in the same ballpark of money. Okay, so some billion less, but it really means that the whole idea of having future collider is unfeasible. And if we want to really develop a visionary and concrete plan that greatly advances human knowledge, this is a project that fulfills these criteria. We are talking about either amazing precisions, both in electroweak measurements and Higgs measurements. Just to give you an idea, the FCC-EE will redo the full LEP1 program in less than an hour. Okay, so this is the kind of improvement that we're talking about. Let me maybe skip this because of time, and let me get to my conclusions. I started by saying that the LHC results had a profound impact in reshaping our views on nature at small distances. And particle physics today is confronting some very deep conceptual mysteries. It's not just, oh, we need one parameter, we don't know how it's coming from. It's more, what is the structure of nature at short distance? How does it work? What are the principles that define that theory? And to address these mysteries, we need a diversified experimental approach. It's clear that not one single project can address all the issues that we have. We need a diversified experimental approach that includes large and small scale projects with different goals and techniques, bridging across fields. I think this is another result of the LHC. It has made us think in a broader way, and out of that came out the ideas for many smaller experiments which are equally interesting to advance our exploration. However, it's also clear that high-energy colliders remain the most powerful microscope at our disposal to explore nature at small distances and are an irreplaceable tool to study the fundamental laws that govern the universe. Also, in this respect, I really want to emphasize that when you say collider, it's not just a single purpose, a project that can do one measurement, but in itself, they are a very diversified physics program. Think of the LHC that can do experiment in heavy ion physics, flavor physics, high energy physics, beam dump. You can use beams in many, many ways. As I told you, Europe is getting ready for the challenge. Thank you. I'm sorry for too long.
Thanks, Gian. Some questions.
There is a question over there.
So, you made some really
Okay. There was also a question there.
You made some really very important. First of all, the speaker was very beautiful.
Thank you.
You made some very important comments regarding the absence of evidence for new physics at LHC, essentially, with the scale, and the connection with the problem.
Yes.
So should we now assume that within the theory community, naturalness is no longer a guiding principle regarding there to expect new physics?
Absolutely not. I think that the naturalness problem is that.
Can you repeat the question?
Sure. The question is now, can we say that naturalness is not a guiding principle for going beyond LHC or the research? And I would say certainly not. I mean, naturalness is an intrinsic problem of quantum field theory. It is linked, as I was briefly mentioning, to a certain view that we have of what physics should be, this separation of scale, effective field theory, which I told you, and I gave you this example of Newton and Bohr to say this is not some strange modern ideas. It's just really it's physics, that this separation of scale. If you accept it, you find these problems and then you want to solve it. We, before the LHC, we thought, well, there is a simple way of solving it. Simple, I mean, there's an interesting way of solving, which is introduce some new dynamics or some new symmetries that do the job. We've seen that that cure does not necessarily work. We still don't know. It's a very confused situation, okay? The simplest version of that do not work. If you try to give a medicine to someone who's sick and you find that that medicine doesn't work, you don't say, okay, now you're cured, okay? The sickness is still there. It just means that that medicine was not the right one. You have to think of new therapies. But at this stage, we are more confused than we were before, in the sense that it could still be that the solution is some of this traditional approach, but in different version, not in the simple version that we started with. Or, as I was saying, the alternative is that we have to look at radically different ways of approaching the problem. But it doesn't mean that we don't have to worry about the problem. The problem is still there. Is this the leading or the only problem in the standard model? No, maybe we should also pursue other aspects which are problematic. But certainly the problem is still there, and it's a big issue that we have to face.
This is a follow-up, but is it accurate to say that at the moment we don't have any prediction for any more specific region of the energy region to look? Because originally naturalness was giving us a guidance where to look, but that's no longer the case.
Well, partly. Within a certain paradigm is still the case, but maybe needs some adjustment. But the novelty, I would say, this is one of the interesting things that came out of the LHC, is that in the recent years, people have tried to think of different paradigms, which are still address naturalness, but in ways which are radically different than the traditional approach. And then they lead to experimental signatures, which are completely different. And then maybe even the collider is not the best way of approaching the problem. So we have opened more directions. So definitely is, depending on your point of view, either a more interesting situation, because now it is not, before it seems that we knew the avenue, so everybody was running in the same direction. It was just a matter of reaching that goal that was there. Now we have there are more open directions, which makes it, especially I would say for theorists, the game more interesting, and for experimentalists more difficult. But still, I would say challenging, because you could have bigger surprises than the one we had before.
Maybe I'll take that first question. So do the plans for a new collider incorporate some kind of Moore's law type thing into the design, where you expect, say, the magnets, for instance, to improve over the long amount of time it would take to...
Right. For the plus and minus version, the technology pretty much is there. I mean, of course, if you talk to the people of magnets, it's like, oh, we have to do a lot of work. But I think conceptually they know that they can do it, they know how to do it, and so the road is clear. When we go to the PP version, then there we really need a big technological jump. And there, so all these estimates are based on extrapolation of what the technology could be, but estimating the time that it requires to reach there is difficult, because we are talking about inventing that, developing the technology. So there are a lot bigger question marks. There was also a question from back there. I saw it. Yeah.
Yeah.
My question was, is the search at FCC, do you have a certain plan to start in a certain, to find something, for example, one of the contestants is WIMP's probability. So do you have a preference list?
Oh, we have preferences. I think whatever we found, we'll be happy if it's something new, okay? I think that it's difficult, the difficulty, but your question is very good, because in a sense is that, before the LHC, of course, the hope was to make great discovery, but there was a clear deliverables that could be given, right? The Higgs, we knew that, either you see the Higgs or you see some other phenomenon, but you know that you are reaching the scale. The same argument was at a certain level also, as was mentioned there, because of naturalness, was also applied to the new physics. But I think most of our theorists knew that the two things are a completely different level. The case of the Higgs is really a necessity of the standard model. There is an inconsistency, and so you need something to complete. While in the case of naturalness, there is a certain degree of flexibility in where the new physics should be, and even if there is. Now, in terms of identifying deliverables, it's much more complicated, because we cannot say, okay, we're going to discover dark matter. For sure, just give us the money and then we'll tell you what dark matter is. No, we cannot do it. All we can say is that, look, we can explore some regions of some parts of theories which are well motivated, and then we can give interesting information about that. If we are lucky, we make a discovery. If not, we still have very useful information to know how to, and we can do that, you mentioned dark matter, but we can do for a long list of questions. We can, we are certain that the FCC will give us useful information, but we cannot promise necessarily any discovery, other than, of course, information. For instance, the FCCE has a very thorough program both for Higgs physics and electroweak physics. Now, that is not necessarily means a discovery, but certainly a wealth of fundamental information about the nature of this particle, which is, I was saying, so mysterious.
Maybe in the interest of time, we can have further questions up front here.
And I'm also available, of course, for discussion.